All right. Well, I've got great news for everyone. After 3 days of NDC, you're not going to have to sit through another talk introducing a framework you feel you're going to have to learn or some other piece of technology you're going to have to adopt back home. My goal here today is merely to make you turn over the apple cart and rethink everything you're doing. That's it. So it's going to be easy. Easy peasy. So, all right, with that, let's get rolling. Easy time here. Sweet. So, back in November 4th of 2010, 2 hours after taking off, Qantas QF-32 landed back at Singapore Airport. Despite not making it to Sydney as planned on a routine flight, it was considered a truly successful flight for all of the 469 people on board, even miraculous. By the time the fire crews had doused engine 1, which wasn't responding to the cockpit and couldn't be shut down, the crew had disembarked and all the passengers, everyone agreed this was a textbook example of modern aviation safety, and what could have been a disaster instead was handled easily and effectively by a highly trained crew and made easier through a well-thought-out aircraft design. But this wasn't a random occurrence. This was the outcome of 80 years of progressive, deliberate action to make aircraft the safest mode of transport in the world today. To think through how we got there and how we can apply that to the work we do in much less stressful and much less human-critical environments, let's back up in time and walk through how QF-32 demonstrated each aspect of modern aviation safety and some ways we can adopt that experience in our own shops through DevOps practices. And it starts out with modern aircraft have an incredible number of performance parameters and events that they monitor and record all the time. Not just as part of the mandated flight recorders or the orange-colored black boxes we all think about, but as part of an extensive system to make sure these aircraft are low cost to maintain, always available to fly every time you need to leave the gate with them. And really, that's not that different than the way we design modern applications, with telemetry monitoring, with different ways of logging, recording events and errors, traffic volumes, capacity, resource planning, and the like. We're not as deliberative as aviation is, but we could be. At the lowest level, the logging metrics in an aircraft then have logic layered on top of them to determine what events the flight crew needs to pay attention to and what priority they are. And this really shows off in what happened on that flight that day. So it's a normal day. It's a routine scheduled flight. They've taken off. They're about 7,000 feet when, out of nowhere, they get a warning out of the aircraft. Engine 2 turbine overheat. This isn't a common warning, but they practice for everything. So knowing the procedure, in fact, the computer shows them what should they do next. They start the checklist procedure for this action. And the first thing that they have to do with this checklist is throttle back the engine in question and wait 30 seconds. That's literally the procedure. See if it'll go away. Now, if that sounds a little bit like turn it off and on again, it's not exactly, but it's not terribly far off. But you know, it's too hot. Let's let it cool down. There's tons of cool air going all over the engine. Let's see if that makes a difference. Meanwhile, after the pilot monitoring starts that checklist, takes the opportunity, because it's his role, to make what's called a pan call. Now, this is basically notifying the air traffic control in the area that we have a problem and it's not good, but we've got this. We don't need any help from you at the moment, but listen and give us some room, potentially. Listen for us to do something. So it's not a mayday. There's sort of a loose understanding of exactly how this works. Mayday is clear the space, I need your attention, I need help. Usually I have to get on the ground right now. But no, this is sort of normal. You notice it's even in a friendly orange or amber, actually, so how bad can it be? Not too long into it, it's about 4 seconds after they started this procedure and they just issued the pan call, things get a little bit worse. As they try to adjust the throttle, engine 2 has what's called a compressor stall. This is sort of like a jet engine backfiring. It's loud, it's noticeable, and it's not good. In addition, it's overheating. That's what EGT, exhaust gas temperature, is too high. And the oil temp is high, which doesn't make a lot of sense at the moment. While they're trying to figure out then which procedure to invoke from here, 2 loud bangs. Loud enough that they can hear them in the cockpit and they can feel the aircraft shake and start yawing or sort of flying off to the left. And then things start happening very quickly. Within 4 seconds, all of these failures, this is 4 seconds of failures, get thrown up on the diagnostic screen. And not only that, but by the way, while I showed them here kind of happening in sequence, the computers in the Airbus are automatically reprioritizing these constantly. They were in the middle of a checklist, that one's gone. It's trying to figure out which of these faults is the most important thing for them to work just yet. And amazingly enough, after these get moved off the screen, it decides, no, actually, we really want you to get back on that procedure. So fine enough, they in that, and what it's done though is that, remember I said there was a 30-second wait? Well, the computer's got to control this when it restarts that clock again. But they'd already they knew how many seconds they were into the event at this point and decided we're not going to totally pay attention to that. We're going to go the original 30 seconds and then try to do the throttle up procedure. At which point they get these two guys, and the second one only shows up transiently, engine 2 fire, but that gets everyone's attention. And followed pretty quickly by engine 2 fail. Now at this point, they start the actual engine failure shutdown procedure, and things get even more interesting. Part of that procedure that they have documented is this point, if you believe the engine's actually on fire, and to be fair, that's not as ridiculous as it sounds, because jet turbine engines are basically on fire when they're running, right? That's the way they go. But this is sort of an unintended fire versus an intended fire. So they go ahead and pull the fire extinguishers. Now, everything on modern aircraft is redundant. And when I say redundant, you're thinking, sure, Kendall, I've seen servers. Servers have redundant power supplies. No, son, we're not talking that level of redundancy here. The depth of redundant thinking in modern aircraft design is incredible. So, for example, each engine has 2 separate fire extinguisher bottles. Each bottle has 2 separate actuators. Each actuator is fed from 2 different systems. All of them failed on engine 2. Fortunately, there was enough of a fuel leak, they didn't know that yet, that engine 2 ran out of fuel and basically died on the vine hanging from the plane. Now, they were then able to work through the diagnostic procedures, work through all the checklists, and about an hour and a half later, bring this plane down for a landing that used the entire runway at the airport, but was successful. They parked, you saw the pictures at the start, everybody got off. Now, that's not an accident. How did we get here? Well, let's start with checklists. So remember I said that first error, here's an error that happened, and how do they respond to it? Well, this is an actual photo taken by one of the supervising check captain on the flight. And in fact, the upper screen there is where the checklists and failures go. And you can tell this is actually from the flight, because if you zoom in, you can actually see this engine's dead, this engine and that engine are very unhappy. Fortunately, this guy's doing a yeoman's job. And down here, they're in the middle of, what you can't read there, is they're about to do their approach, and it's basically abnormal approach, which is, I love the understatement in some of the messages. We have normal approach, and then, things are a little off, like there are holes in the wing. And underneath it, you actually get the detail of anything you want to pull up and things you can work. And right now, it's cheerfully listing all the stuff on the plane not working, and then the little thing here telling you there's yet more. So, but it's all good. It's all straightforward. Let's look at an example of one of these in-flight checklists that they actually work. So this is interesting. This is not from that flight, because unfortunately I don't have any checklist pictures from the flight. I know, it's rude. They had 5 people in the cockpit. You'd think one of them could have been taking a bunch of pictures. But nope, I guess they were a little tied up. But this is actually from a result of a different aircraft accident, AF447. This is a revision that Airbus made to a checklist. This is one of the submission photos they used to prove the revision. But basically, here's the fault. Unreliable airspeed indication, meaning we don't know how fast the plane's going. And then a helpful checklist of what to do. All right, so if you're really worried, check that the autopilot, the autothrottle, the flight director are all disconnected because they're all computer driven. If they don't know how fast the plane's going, they're not going to do helpful things. They might do unhelpful things, but they're confidently not going to do helpful things. Set your throttle levers to climb. They love their abbreviations. And then we want you to basically pick, depending on how tall you are, how high up you are, angle the plane up, pitch the plane up to a certain angle. And the reason that they do this, by the way, this is a procedure that was evolved because, in essence, no matter what, this will result in the plane stabilizing somewhere in a valid flight envelope. It will not go too fast for its height. It will not go too slow. It won't stall. If you don't have any idea how fast you're going, you can basically set the throttles to a certain position, pitch the aircraft to that angle, and you can continue flying long enough to figure out what to do next, which is sort of the first goal, right? In fact, in aviation, there's a sort of a classic mantra, which is aviate, navigate, communicate. First fly the plane, then figure out where you need to go, then tell others about what's happening. And that, by the way, is a very good mantra to think about in your own shop for operations. When you have an incident response, when you're trying to keep your systems up or respond to something that's going unusual in your system, it's basically first work the problem, then figure out where you need to get the systems to, and then worry about communication outside of the team working the problem. So when there's a fault at the flight crash address, they have to work this checklist from top to bottom. This, by the way, is a very Airbus-specific design. Boeing aircraft use a slightly different mechanism, but it's very similar. It just has somewhat different rules. Each aircraft manufacturer, for very good reason, sort of involves their own rule set of the way this works, and pilots drill on this stuff in the simulator all the time. I say in the simulator because, fortunately, it's extremely rare to get any of these events in the real world. All right. So a checklist is designed then that you can work through things and you know what you need to do. Now, it's not an instruction book, right? So, for example, risk of undue overspeed warning. They're just letting you know, hey, the plane may start complaining to you. That's a risk that's going on. Nothing for you to do at. It's not telling you exactly how to carry out these actions. This is not meant to be a complete, exhaustive set of instructions. It's meant to be enough to trigger your memory and training about what you need to do. A basic structure of a checklist, the best research shows, is a structure called challenge, do, verify, CDV. So challenge. This is the thing we want to do. Like, we want to arm our speed brakes. This is common coming into landing. Set them up so that they will auto-deploy as soon as there's weight on the landing gear and we're on the ground. Do, so the person that's not calling it out arms the speed brake, says that they did it, and the other person visually confirms that they've done that. Now, you notice that this is a teaming or a pairing approach. And that's a core aspect to effective execution of checklists, is this isn't just one person doing it. This is a person communicating what they're doing, and the checklist becomes a means of that. So as one person's accomplishing an item, they're saying what they're doing, the other person's confirming it, and between the two of them, they have high confidence they're taking the action that they meant to take. Now, let's turn around and apply something like that to a risky operation that we would do, maybe in our own data center. Let's say, for example, that you need to recycle or restart a server. So let's think about a checklist for a basic server restart procedure. First thing is, let's confirm we're actually working with the right server. I've been ops for a long time. I cannot tell you before we literally institute a checklist procedure how often we turned off the wrong server. If you've ever seen a rack of 24 servers top to bottom, and you start saying things like, it's the fifth one down, but from the other side of the rack, it's not the fifth one down, interestingly enough. Things like that. So confirm the server identity. Yep, we know it's the one we're meant to be working on, and we have selected the right one. Confirm that we can restart it. So for example, if it's part of a cluster, do we know that there's other load in the cluster, other servers in the cluster right now that can take the load we're about to present with it? Or are we going to overcapacity the cluster by taking the server offline? We need to then drain stop it. Let's say it's a web server, for example, and it's taking requests. Well, we don't want any of those requests to fail. If we're doing our job well, we want to basically keep it from getting new load, let it complete what it's done, and have a specific thing we're looking for. Now, you notice here, by the way, this doesn't just say, confirmed. It's a specific thing we're looking for. There are no more requests running on this server. Then we go ahead and actually restart the server, and that's completed because we see that the OS has come back up. And then we actually want to verify that the services on it are running. And that ideally in a real checklist would have something more specific, like for this system, this is the set of services that we mean to run. Checklists can have sub-checklists. And then finally, start giving it load, and we would know it's taking load because we see requests are greater than 0. So you might think of something really simple, like, yeah, all I'm doing is just restarting a server. But as a team, if you take the time to talk through what's the right procedure for that, what's a checklist to make sure we don't make a mistake as we do it, restart the wrong server, take out a server that's still under load, put a cluster under too much load while we take out that device and restart it, think it's restarted, but only 2 of the 3 services it ran came back up, so we start passing it load before it's ready to go. Or we think we did it, restarted it, brought it back up, but forgot to add it to the cluster somehow, some way, and so it wasn't actually taking any load, and we weren't as redundant as we thought. Each one of those items I just mentioned is literally a mistake I've made. And checklists are a way to keep yourself from repeating mistakes of the past and give you time to think through a good procedure when you have space and time, not when you're in the thick of it. So there are also ways you can apply this to abnormal events. We're even talking about a normal event, and pilots have a ton of procedures for the before engine start checklist, the before takeoff checklist, after takeoff checklist, climb power checklist, etc. Some of them are super short, some are very involved, but they also then have them for abnormal events, which is where we started with QF32. Let's say, for example, you have a problem with the server using too much memory. You can make a checklist for this. What's the actual primary consumer of memory on that server? Is it actually wrong? As in, is it just that it's under a lot of load, so the memory utilization is high, but it's not wrong? We're just getting a lot of traffic right now? Or do we actually have like a memory leak? And now, of course, in here it's not an instruction. I'm not telling you how to check that. That's something your team practices. If it's abnormal, like it's a leak, then we should probably recycle the process, restart it, and see if that clears it. Either way, then, we should monitor the service for a period of time and decide, is it going to go back down? Like, is it a load and it's resolved itself? Or did it go right back into the scenario? If it's a defect in our code, it might go right back into an error scenario, in which case, even if it was just high volume, we might recycle that. So creating and adopting these checklists isn't an individual sport. It's a way that you can, as a team, talk through how are we going to respond to something, and do so when you have space and time to think about it well. It's also something you can revise in response to an event. When you have an issue, turn around and take the time to say, how could we have handled that better? What would have been handy to have in the moment? What's something that we could all have access to so that whether you're senior or junior on the team, we do a good response? And practicing the idea of ops pairing so that we're working together to solve the problem. But working together goes beyond just pairing on checklists. In fact, the core safety discipline of the latter part of the 20th century was an idea called crew resource management. So initially, when we think of airline pilots, we think of this guy. Glamorous captain. I know you can't see his stripes. He's not actually wearing a captain's uniform here, but glamorous captain, king of all he surveys, gets to do whatever he wants. And traditionally, you go back into the early parts of commercial aviation, captains were absolutely at the top of their stack to do pretty much whatever they wanted to. Now, in most airlines today, you'll still have the rank of captain. And then you also have first officer, and that is, one's more senior than the other. In fact, if you ever want to know, top tip, count the stripes in almost every aviation uniform. 4 stripes is captain, 3 stripes is first officer. Depending on the airline, there'll be different colors. But the key thing to understand is that that's sort of a rank designation. That's not their role on a flight, and that's not an indication of how much training they have or any of that. That's basically the same. It's more an indication of progression of their career and time in service in a particular airline or on a particular type of aircraft, et cetera. So while we traditionally had the captain was essentially king of the domain, got to do whatever they wanted to do, they were treated as responsible for the entire aircraft and had absolute authority over its operation before we adopted crew resource management, or CRM, because of course no 3-digit thing can be unique, right? So for today's talk, it's not CRM is crew resource management. The captain was considered the infallible senior crew officer. Typically flew takeoffs and landings, the interesting parts of the flight, and the first officer was there for secondary activities like radio communication, navigation, system monitoring, and the boring parts of the flight. Every once in a while, captain's prerogatives, like, yes, you can take the takeoff today, why not? But a string of incidents in the 1970s turned this over and totally changed the thinking around it to create what was originally called cockpit resource management and became crew resource management. So it started off in sort of actually the seminal incident that really kicked this over is an incident in 1970 on an Eastern Airlines L1011, that's actually the incident plane right there. This plane was brand new. It was 4 months old. And so actually both the captain and first officer were relatively new to that aircraft type, but the captain had an extensive experience, and they were operating in that mode. Captain sitting on the left, first officer on the right. And they were on approach to land in Florida. When they were doing this, they lowered the landing gear. Now, at the time, the CoPilot was flying, and the captain sitting on the left lowered the landing gear. But when he did so, the three green lights tell him that the gear are all individually down and locked, didn't all come on. The one for the nose gear didn't, and that's in this quadrant right here. So that's where we have our gear handle. This shows the down position, and that shows what he wanted to see, 3 greens. But he didn't get the middle green. He didn't get anything. Didn't get the red one either. He got nothing. So the captain and the started trying to troubleshoot this problem. Why won't this light come on? Now, they're flying in the dark, and that's not a very convenient position. This is not a small cockpit, left to right. And you can see that that's sort of on the right side of it. So what actually happens is, while he's focusing in on this control and this light, and they literally start disassembling the light so that he can see, like, is the bulb broken or not, and check it. He's trying to figure out, is the gear down, because he can't get the green light to come on. He bumps his control column forward, just a little bit, just a little bit. And what happened is that gave the plane's autopilot a slight descent. Now, the right-hand person, the co-pilot, was flying the aircraft, but because this was on his side of the plane, the captain was actually giving him instructions to fiddle with the light. So instead of actually flying, he was messing around with this light. And basically, they did not notice that they were descending until far too late, and actually impacted with the Everglades. When they dissected this through, what they saw was basically a fixation on a problem that occupied everybody, and nobody was really taking care of flying the plane. They did not effectively utilize the people that were there in the cockpit. And out of this, they then said, look, traditionally we thought of it as pilot and co-pilot, captain and first officer, and it's a hierarchy. But really what we need is you need to have peers. We need to have a way so that when responsibilities are delegated within the organization, somebody's always focused on flying the plane. For sure, that's what they're doing. If there's a problem, someone else is working the problem. And a challenge is something in the language even. We refer to as pilot and co-pilot. To effectively work at the team, we need the players to feel like and act like peers. So one of the original recommendations out of cockpit resource management was, you know what, we shouldn't refer to it as pilot and co-pilot, because it makes it sound like the co-pilot's just the secondary sidecar. Let's refer to it as the pilot flying and the pilot not flying, to make it really clear that somebody's flying the plane. And you notice that this isn't rank. This isn't captain and first officer or whatever, but it says at any one point, there's somebody flying the plane. Now, even then, more recently, they've discovered that there's a little bit of challenge in this language, and language matters. Is that what you're doing? You're saying pilot flying, pilot not flying. Well, how many folks think that someone trains for the tens of years it takes to be a pilot on a long-haul aircraft and likes to be referred to as the person not flying? That's what they got their whole career. They wanted to not fly, but just sit in a really cramped seat in the front of the plane. Nope. So instead, the latest thinking refers to it really as pilot flying and pilot monitoring, because it gets to the point of what you're asking these two people to do. And we've actually really clarified the responsibilities for these two sides. So the pilot flying manages the flight path, in other words, knows where he's taking the plane. But the pilot monitoring monitors, are we going where we said we were going to go? The pilot flying is managing the aircraft energy. So you think about an aircraft at altitude, what you're always managing an aircraft is the energy, basically the kinetic energy of the plane. You're going a certain speed, a certain altitude, and you can always trade height for speed, you can trade speed for height, you can make different trades at different times to, given that you have energy in the plane. So sort of energy is room. If you lose an engine and you're going quickly, and you're high, you have tons of times to deal with it. If you're very low, you don't. But the pilot monitoring monitors aircraft energy, particularly in key phases of flight like approach. Are we getting too low and slow so that we can't recover from a problem, or we may get ourselves into trouble because we've let things decay too far. The pilot flying flies the aircraft, but the pilot monitoring those system states, handles communications, and calls out to the pilot flying deviations. Now, again, this is not a hierarchy. This is a team. And that's really important, because the pilot monitoring has an obligation to basically say, in essence, we're in an unsafe configuration. Here's an action, we need to take action on this. And that's essential, a part of teaming, an essential part of not thinking of it as a hierarchy, but as we are collaborating. Because I may see something you don't see. And so either I may need to take control if what you're doing is unsafe, or I can't communicate or react fast enough, or I at least need to get your attention to what we're doing. Now in QF32, they were both lucky, they were lucky. They had 5 people in the nose of the aircraft. This is now only, I think, on an A380 could you actually fit 5 people in the cockpit. But they had the captain and first officer, and for the flight we're talking about, the captain was the pilot flying. Doesn't really matter, could have worked either way, and the first officer was pilot monitoring. But as the problem progressed, they used everybody that they had in the room. And they did it through a sequence of the way their training unfolds. So for example, as soon as they realized, they heard the bangs, saw the behavior of the aircraft change, realized that there was a real problem, the captain didn't get out his flight goggles, throw back his scarf, and say, I've got this. Instead, they discussed as a crew what their actions were going to be and what they were going to do next, and started delegating tasks. So for example, the captain delegated almost immediately to the supervising check captain public address and working with the cabin crew. The difference between sort of cockpit resource management and crew resource management is recognizing that you have a group of folks behind you in the cabin, and they're part of the total crew. They need to keep apprised of what's going on so they can react to it. I mention that because when you're doing an incident response, so for example in your organization, there's not just your team trying to resolve the problem. You have your customers, you have your customer support folks, you have the rest of the business that you serve, and at some point, they need to be kept in the loop so they understand what they can and can't do to not make the problem worse, what they should be communicating out to customers. Customers, if told there's a problem and when they can expect it resolved by, are much more amenable than when things are just broke, right? So, but that's an activity and an action that obviously you don't want to have fault just to the person trying to fix the problem. And they delegated some other things out. So they had a second officer. Now, that's not a common rank in aviation, but Qantas uses it mostly for basically a designated cruiser relief pilot, because they're doing very long flights in this aircraft. What they had the second officer do is go back and do damage assessment. They knew, you saw the field of red, and frankly, they didn't entirely believe it. So the second officer walked back through the center of the plane and looked down onto the wings to see what he could visually confirm and verify. Came back and reported back what he saw and what he thought it meant. The check captain, check captain was there to actually check that periodically every captain, line captain, has to have someone double check that they're really flying safely and correctly, not just in the simulator when everyone's watching, but on the flight deck for real in a real flight. So the check captain was checking the captain. The supervising check captain was checking the check captain because it was up for the check captain's check captain check. And so that's why he was there. So it's kind of pretty epic that they actually had these 5 people there, all of which had a lot of time in the aircraft. Interesting point, guess which one had the most time in an A380 at this point?
Supervising check captain.
That is correct. Who had the least?
The captain?
Yep. The captain only recently transitioned, had only a couple of hundred hours in the aircraft. The first officer had well over twice that. Everyone's trained in simulators. By the time you're actually in the aircraft and flying it, you have a tremendous volume of experience in the way the aircraft work and the systems work. And in fact, one of the things that they were starting to discuss when they saw the messages is they could see that both hydraulic systems were marked as faulted. But they knew from the second officer's observations there was only the number 2 engine that was affected, and that was the one that had obviously exploded and been shut down. And that drives only one of the 2 hydraulic systems. They couldn't believe why the second hydraulic system had failed. They started doubting the diagnostic system. So as a group, they communicated amongst each other and said, okay, what can we check to verify that the diagnostic system is at least trustworthy enough that we should take it, that what it's saying is the case, and try to fly the aircraft as if all those inoperative systems are really unavailable. And because of all of their extensive experience in knowing exactly the way the aircraft is set up and designed, what feeds what is connected to what, they worked out a couple of quick checks that basically the captain, the pilot flying, was able to do to confirm by just control inputs that, yep, what it's saying has failed, we don't have access to anymore. Now, on an aircraft, losing both hydraulic systems is not a good thing. But they have redundancy after redundancy. Now, in the case of some aircraft, they have a 3rd hydraulic system. The A380 doesn't. It uses, for weight-saving measures, it actually uses electrical actuators for the actual control surfaces. There's a backup to the hydraulic ones. So they all still work, and they did some very gentle maneuvers to confirm that they could still control the aircraft, but they can't move the control surfaces as quickly without the hydraulic pressure. So they knew that, and they worked that through. But it also meant that they lost certain things. They lost anti-lock brakes. They lost brakes in some of the landing gear. And this led to another challenge, which is that the check captains started running configuration checks to say, when can we land? Because pretty much their goal was work through all the errors, get the plane on the ground, get the passengers off. All's good. The challenge is that the computer's telling them that they can't land at what they know to be the largest runway in the area. And so they keep running sort of simulations because they're overweight, which is very typical for flights. Believe it or not, a lot of long-haul aircraft take off too heavy to technically land back. They either have to dump fuel or do an overweight landing, which then requires additional maintenance checks and expenses, and they don't want to go through that. So they kept running through simulations through the computer, which is what the check captain was doing, to try to figure out, could they land, if so, with what margin, with different things operable and inoperable. And they were getting basically weird results out of the software, which I'll hit at the end. And they ultimately basically were able to give it a configuration and make a certain level of assumptions they were comfortable with, and it showed that they would have something like 100 meters of spare, 150 meters of spare space on a 5,000 meter runway, and thought, good enough, that's the good we're going to get. But they also know that as time's going by, they're burning jet fuel, and jet fuel is weight. So on one hand, they're getting better over time as they're in the air because they're getting weight. On the other hand, they have holes in the aircraft. So we want to balance these two factors. Complicating it is they've lost other systems, so they can't transfer fuel. So they know that there's kind of a clock running on them because they have one engine running on one side of the aircraft, two on the other side, and they can't transfer fuel effectively between the two wings. So the aircraft's balance is shifting over time. And at a certain point, that becomes a problem. So that's a lot to take on. But in fact, even though they had all these extra people to help them out, they take advantage of everyone that they had and did it through a process of making sure everyone was involved in the decision and knew the status of where they were each time they're making a decision, also knew when they were going to revisit decisions. So they basically revisited through the decision many times of, should we declare an emergency and just land? Or should we stay up here, go around again in the loop, burn more fuel, and keep working the errors down? And they elected to work basically through the error list to get it down because they were confident on the whole group that they could basically, that the plane was in a safe configuration. It's worth pointing out that subsequent studies proved that even if the whole group of lower three had not been there, just the pilot flying and pilot monitoring could have executed all the operations they needed safely and selectively, but they didn't have to, and they leveraged the extra people that they had. So let's turn around and talk about then how we operate as pairs and teams. Think about a moment of the idea of an engineer acting and an engineer monitoring when you're doing a risky change, like deleting a database, taking down a server, deploying a new system. Think about then the roles of these two. The engineer acting is managing an execution plan, and you have a plan, right? So you don't just go out there and mess with things, right? Have a briefing ahead of time, have a plan for what you're going to do. The engineer acting is managing that plan. The engineer monitoring is monitoring step by step that plan is what we're actually doing. The engineer acting selects tools and methods that they're comfortable with. So, I want to do this from the command line. I'm going to do that from this UI. I'm going to use, here's the script we're going to run for this. But the engineer monitoring looks and says, yep, I agree that tool's doing the thing you think it's doing and is a safe way to execute that operation. The engineer acting is executing those changes, but with the engineer monitoring, confirming those changes, handling out communications, and looking for risks or problems, and doing so in an assertive way. So there's a lot of pieces to total CRM, and I've talked about just two aspects of it, but overall it's encompassing the notions. And you can go look at crew resource management up. There's a lot of research on the subject, and as you read through, you think to yourself, as we're trying to do different complicated things, there's a lot of good here. There's a lot of good ideas we can assimilate. Ideas around team leadership, briefing and planning. In other words, talking through what you're going to do before you do it, even routine things. Before they push back from the gate, pilots always have a briefing for that flight. And no, it's not what you're hearing over the announcement. Yes, today we're flying to Sydney, and we're going to be allowed to 32,000 feet. No, not that. They're actually going through the entire sequence of what they're going to do and what they expect are issues, the way they think they're going to get to the runway, anything that they need to do to execute that flight correctly and safely. And it's a way of just double checking and getting yourself in the mindset of doing a dangerous operation. Decision making as a team, how you flow and decide what the right course of action is at a moment. Shared situational awareness, so the whole team working a problem understands where you are on the problem. Ability to react to new challenges and problems, how to advocate for the needs of other team members while you're doing things. If you have something complicated going on, you don't want one side getting ahead of the other. If you're doing a complicated deployment that's data stores and other things, you don't want to kick off one part of it before, say, the backup has completed. So we need to be aware of where we all are and advocate for people that are not necessarily involved in the current conversation to make sure that what they need to have happen happens. We're checking how we're all doing together. This isn't an issue of not trusting. It's an issue of assisting and making sure that we know how we're doing as a group, which decomposes into how we're doing as individuals. We're communicating in a style that is, again, is informative and declares the state of where we're ending up. Think about the way that checklist was structured. This is the goal we want to have. I'm achieving that goal this way. Yes, the goal is now achieved. I'm clear from the initiation that it's done and it's come back. The last item that I find interesting, because I've seen this problem in teams, particularly where you have a spread of talent, is assertiveness. Someone sees something that's not right, and this could happen at any phase. It could be while you're planning, it could be during the execution, it could be during a recovery event, but they feel that they're junior, or for some other reason they don't feel that they can get your attention and speak up. And this is one of the other things that's happened significantly with actual accidents and flight crews. So there's a basic pattern that's been proposed for in CRM for a 5-step assertive statement process. That's a way to basically get people's attention without having to be shouty, yelly, dramatic, invoke hyperbole, things like that, and in a way that moves the ball forward. So it goes like this. Have an opening. So, hey, Dave, I think we're going to run out of disk space if we restore to the production server, because the production database is over 4 terabytes, and I don't think it's going to fit on that system. So why don't we go create a temporary SQL server in Azure, and we'll run the store there and grab the little bit of data we need out of it. Does that sound like a good plan to you? Now, nowhere there did I sound, like I'm asserting authority or questioning your judgment or anything. I've spotted a problem. I've stated it. I'm giving an idea of a solution that I'm not married to, but should solve the problem, and trying to get agreement that this is a good course of action. And it's a pattern of flow that you can use to, basically without rank in a team, communicate a challenge you see and an opportunity to do it. And the outcome of this might be you get down the bottom and say, well, let's not do that, but let's do something else. And then if you're comfortable that solves the problem, great. If you're not, well, wait a minute, here's this other challenge I see with that. What about this? What about this way of compensating for it? So you wouldn't think, like objectively, sit back and think, well, of course, this is just natural team conversations, but we're all people, and people have egos. People get tunnel vision. They get focused on a particular solution. They don't always pay attention to outside input and take that on. This is a way of getting that attention. What this really came out of is there were 2 incidents, again, in the late 70s. One was in the Portland area where, in essence, a pilot, this is, again, before the CRM model, so a pilot flying, pilot not flying, the captain who was flying got so focused on why one of the landing gear was not confirmed down that he kept circling near Portland until the aircraft ran out of fuel. Despite in the CVR hearing the flight engineer and the co-pilot saying, don't you think we should go to the airport now? Fuel status is only this. I think we should turn towards the airport now. But they never really were getting his attention, stating really clearly the impact of the problem they see, which is we're going to run out of fuel and crash, and getting his buy-in on a course of action. And so that became a standard part of sort of assertiveness training, because people, it's not because of authority, it's because people get very solution-focused on the problem they're working. And you can imagine this happening exactly in a data center. You're focused on one problem you're working. Like, hey, this server's, the batch system's going down, it's doing this thing. We're not able to run things through it. And you start doing ever more escalating things. At some point, you might actually start causing a problem for something else. I had this problem recently in production. They'd taken the batch system offline. They were recycling because they're using too much memory. They kept recycling it over and over again. And I'm starting to point out to them, requests are queuing up. The queue is only so big. Very soon, we're going to start rejecting business. And it's all fine and good until you start rejecting money. Then people get very concerned. So at some point, even if it's not performing well, perhaps we should split the cluster, let half of it try to run, basically run but run badly, while we triage on just part of it, what's really going on. All of this information we have about aviation, and those who know me know I could go on a long time about different things you learn from aviation and the fascinating lessons, is the result of rigorous incident investigation that's been going back a very long time. And what's amazing about it as an industry is the level of transparency. So the final report for QF32 is 400 some pages long and goes through everything, even covers things that worked right. And that to me is fascinating because if you ever had a production incident or something, for example, at the end of a sprint we do a retro. But if you think about production actions like production deployments or incidents you respond to, you might go through and do a root cause analysis to give to customers that's purpose is to sort of make you sound like, yeah, you've done something to keep this from happening again, but you weren't idiots. There's none of that kind of emotional liability in an actual incident investigation. So it's a practice that you can actually pull in, even if you just use the results internally, so you can learn from them and the whole team can learn from it. So what do you investigate in an incident investigation? Well, you look at a number of aspects. The organization, because nothing happens in a vacuum. Your incident that you reacted to happened within your corporate organization. The operating environment. So, in other words, what time was this? Where maybe you're working with the cloud, and it was this situation in this data center. You guys were in this data center. What are the things around the space that you were operating on? The specific occurrence itself. Like the timeline of things that happened exactly, who took what actions, what did we see, what notifications were raised, what communications were made, all those pieces. The human factors involved, and this is a huge part, this is where the CRM came out, but what were the people things that led into this or away from it? And then aspects of the system design itself that influenced the outcome we got. Now, in air accident investigations, there's actually a number of other ones, but they simply don't apply to DevOps, so I've kind of trimmed them out because the list is always like that. But these ones really do convey. So when you think about organization, there's the 6 M's model here, and this is actually right out of the U.S. federal government's aviation investigation standards guide. But if you think about it, this applies to basically the same thing that whenever we do a DevOps step. Overall, even if we're not in a company, there's ultimately funding around everything we do. There's an expectation of either money coming in, money going out, the resources we have available to us, and the pressures that creates to perform. Maybe you, for example, feel in your organization a tempo that says, we have to deploy this often. We are a CI/CD environment. We deploy constantly. That's going to create a bias in you to not want to hold up a deployment. That creates an expectation of deployment in your situation. Within that, then, you'll notice the overlapping circles in the interior, and because this is literally a screenshot, I've left it as man, and otherwise it's 6 M's, but the person, the medium, the machine, and the mission, and how they come together. The reason those are overlapping is because the connections between them are the really interesting parts to look at in terms of how they affect your organization. Because you put specific people on that problem. They had specific hardware or software that they were working with. They were using specific tools. They had a specific goal. All those elements come to play in the organization. It sets the stage for how they're going to respond to the incident, what acceptable results look like, et cetera. So when you think about operating environment, I'm going to drill into a couple of these. So state of the systems. When the incident started, were you fully up or down? Maybe you're in the middle of an upgrade when an incident started. And that's an important precursor to think about in terms of how you respond to the problem. Maybe, for example, you deployed the day before, so all of the A-team were in bed when everything went wrong. And it was just sort of the luck of the draw, or over a holiday. What procedures and practices did you already in place? What were the standards, expectations, and conventions when things started? People are going to act from those conventions, so if you look back and say, well, they did the wrong thing, but if that was the procedure they had, there's a good reason why. What prior events had the organization had that sort of taught them a reflexive action? Prior event could be as straightforward as things like not just an outage, but could also be like 2 weeks ago we'd had a critical production outage. We were down for a full day. So right now everyone's on a hair trigger looking at everything. So we saw one side thing and then overreacted to it. That context is really useful to evaluate what you had. So there's a number of elements that go into the operating environment that the problem happened in. For the specific occurrence, who was involved? What kind of planning and briefing did they do? I'll tell you a lot of the times when I've been involved in incidents, I discovered that on the IT side, there was almost no pre-discussion of what they were doing. What was a routine deployment? Well, yeah, but you routinely replace the entire production environment. That's, just because you do something often does not make it routine and trivial. So did they actually plan and brief? Who was going to do what? We had a production incident recently where 2 people tried to do the same task at the same time. Didn't realize it. No one was doing the other task. Because they didn't brief ahead of time on who was going to do what. And someone thought, I want to do this bit now. This bit sounds more fun. The exact timeline of events, what happened when, and it may be things you observed or didn't observe. So we think about, for example, the QF32 incident. There was information being recorded in the electronics in the flight recorder system and the diagnostic system well before the actual problem came to pass. How effective were you, and I like the term here, but how effective were you at crew resource management? When the incident happened and you had to respond to it, did the team work as a team? If so, who got what role? Was that effective? Were those people adequately trained and practiced to handle that role? Or did we, for example, hand someone a role they'd never done before and then act surprised when it went badly? Finally, how do we communicate about the incident at the time? Again, it's easy to forget it, but the way you communicate outside of your structure is critical to the effectiveness of the entire incident response, even though you're thinking about how fast do I get the systems back up. But that's where CRM comes into play. No one person dons their flight goggles, throws the scarf over their shoulders, and just goes for it. You work as a team. Human factors are probably the most delicate bit to discuss as an organization. And it's amazing to me to read through the incident reports for aviation, just how far they go into the human factor side of it. And that's partly because modern systems are so reliable and so redundant that the human factor is sort of the dominant part of that. So with human factors, we're trying to determine how breakdowns in human performance can cause or contribute to an incident. And that doesn't mean, by the way, we're not talking about blame, shame, or any of that. We assume that, that there was sort of good intent. It's a dispassionate examination, but we don't presuppose malice or anything like that. You can get there, but we don't. Now, there actually are a couple of formal models for this. I put them in the slide mostly because if you're really curious to dig into how this is done, these are the quick things you can Google. The first one is the shell model, which is a little bit older. It focuses on the interfaces between people and software, and people and hardware. And then how those things connect together to have caused the actions they did. One of the reasons that that's really important is the fact that the people are rarely the exclusive cause of the problem. And I want to hit something just as a side that next time you'll hear about on the news and they say, like, okay, we've completed this incident investigation of this particular aircraft accident, and the result of it was pilot error. As engineers, every time we hear the phrase, it was pilot error, we should cringe. Because what that really means, the vast majority of the time, particularly in commercial aviation, is that the computers, the systems, the technology presented a vision of reality to the pilot so convincing that they literally bet their life on it and lost. Pilot error means we failed them, not the other way around. So yeah, the pilot did the wrong thing, and they were so convinced to do the wrong thing by the aircraft that they bet it all on that. And I mention that just because it grates on me when people, well, you know, what can you do? It's pilot error, I guess the plane's fine. No, that's a failure of human-computer interaction. And as we do more and more with technology, that's going to come up in more and more places. It's going to come up in Teslas. It's going to come up as we automate all kinds of other things. It's going to become a bigger and bigger factor in what we do. There's another model that is a little bit more modern and is useful from a counter perspective. And this, I think the shell model applies a bit better to DevOps if you go look it up. But the other one's called reasons model, and it's often sometimes referred to as the Swiss cheese model. And it basically says that in essence, organizations or each layer of the process is pretty good, but has small holes in it. And the real challenge is when all those holes line up, so there's actually a path all the way through that gets you to the incident that happened. That lines well with sort of modern aviation challenges, but a little less so. I think we're not nearly as rigorous in what we're doing, and so the shell model is a better mode. All right. Reasons model goes to these 4 items. Organizational influences, unsafe supervision. So your organization might say, we have to ship all the time and ship quickly. Unsafe supervision, meaning that we put someone maybe without the training or the adequate backup into a position where they couldn't succeed. Or they actually themselves took an unsafe action. So in other words, they maybe they just made a bad decision in doing what they were doing, or they were careless. Errors and violations. So this is sort of the sub-thing of trying to understand why what they did was a problem. So if you go look this up, it's an interesting taxonomy for why things happen. So finally, system design. You'd think in IT this would be the biggest piece, and certainly a piece, but a big part of it just comes down to, when we talk about system design, did the system operate as designed and failed? So in other words, we didn't design it right. So like maybe when overcapacity fell over, it's not that it was defective, it just wasn't designed to handle what we gave it. And then when we think about reliability versus system safety. So reliability is, did the system perform as designed, versus system safety, given how we use it, is it a safe system to use? So if you think about defaults and applications, we had a situation happened to us once where we didn't realize it, but the default button on a form that only our customer service folks had access to happened to be the delete this customer and all of their data button. This only came up when someone actually used an iPad from Disney World to try to do a change on a customer. And you know, an iPad will automatically give you a sort of a text like go sometimes when it sees like that should be a thing. And they click that, which activates the default button on the form, which was delete the customer. And only when the request took a long time, and then they ended up back on the home page, they're going like, wait, that's not right, did they realize they just expunged the customer with 4 separate repositories in our platform. That's not their fault. That's an unsafe design. So here's another example of where a learned experience has modified a design based on an actual outcome of an investigation. So this here is the checklist for on an Airbus aircraft for manual fuel balancing when the automatic balancing doesn't work. And it's different. It has a key top step in it didn't have before. If no fuel leak. And that happened after an incident where basically to keep balancing, because they were getting out of trim warnings so that the wings weren't balanced, they kept transferring fuel from one wing to the other, couldn't quite understand why the one wing just kept getting so light. Assumed there's just some reason for it. The reason turned out to be a massive fuel leak in the dark in that wing. And they ran out of fuel over the Atlantic and glidered for 18 miles to a totally safe landing that everybody walked away from. But the outcome of that was not, whoa, woohoo, it's a glider. It was, we should have something in the checklist that says, by the way, before you just go start transferring fuel all over the place, why don't you confirm there's not a fuel leak? There's not a reason that there's this imbalance in the first place. So all that brings us back to then, let's talk a little bit about the post investigation on QF32, because you wouldn't think I'd lead you all this way through Qantas Flight 32 and not tell you what happened, right? That would be a little cruel. So what the pilots didn't know a little bit after takeoff is that this little pipe right here developed a fuel leak. Now this is deep inside the engine. So if you look at the picture here, if I'm a jet engine, here's the large front fan. This is about right there on the back before it fattens up again for the back edge. It's after the hot section of the turbine where the fuel's burned. So the air that's flying by, this right here, is very, very hot. This section is very, very hot. All the things you see in pink are actually air-cooled sections. So since they're air-cooled, there's a lot of air moving through them. Now when I say cooled, let's just put it in perspective. The normal temperature around here in flight's about 380 degrees. So when the fuel leak started, it spontaneously ignited. I should say the oil leak started, it spontaneously ignited. Now, you may be surprised, but the jet engine was not intended to have, fire here. That was not in the design goals of the system. And so what happened then is that progressively burned through both sides of this. When it did so, it started breaking loose in the seals. Now this part right here, that you see in gray, this part is spinning very fast. This part is spinning very, very fast. So it broke through and actually started allowing this hot gas to enter and blow by it and going through here, making all of this that much harder. The next step that happened was that little bit of metal right there failed because of the heat, And when it failed, this is basically a giant metal disc. When I say giant, it's about that, with then blades beyond it. The middle bits that held it to the drive shaft, because what this thing actually does is it takes power out of the air, basically, and it routes it back to power the fan blades on the front of the engine. And it broke loose from that. Now, when it broke loose, it acted like a pinwheel. It just started spinning faster and faster and faster and faster. Interestingly enough, no detection for that. That's not a thing that was monitored because that should never be going faster than the shaft it's connected to. And within a few seconds, it shattered into 3 pieces. In fact, within about 3 seconds, it shattered into 3 pieces. Those pieces flew out radially. The significant bits, the biggest chunk went that way, and then this one went right up through the wing. This is interesting because it's sort of a really lucky shot. 2 ways. One is none went between that angle, which is fantastic. The plane was only 7,000 feet, so it wasn't really pressurized, but still, big, hot hunk of metal flying through an aviation cabin is not considered a normal procedure. This bit, though, is a real problem because it intersected with this air fairing down here. And that is where the vast majority of the faults came from because it literally sliced one of the largest bundles of cables in the aircraft right apart. Not a failure mode the plane was designed to understand. So this caused the vast majority of, in fact, the warnings you see where they couldn't control and couldn't access whole tons of systems because you're not getting through that. That's a problem. So they were able to go through, dissect all these pieces, understand all the different elements of what had gone wrong, and trace it back to a very small mistake. The stub pipe that broke had been slightly misdrilled. So one sidewall of it was thin. And that was fine for a certain number of flights, a certain number of hours, but the vibration of that part of the aircraft was enough to eventually crack it, just enough that under pressure, oil shot out of it. When they went back as a result of the accident, they then came up with a set of safety recommendations. And this is something you should do too. When you go through an investigation of what happened, you should look at things that went right, the things that went wrong, even in things that are not exactly in the area you're in. Because you're taking an opportunity to look at to complete dissection how your system ran. You're probably going to see things that aren't directly related to what went wrong, but are still a challenge. Maybe it was poor error messaging that was confusing, or a lack of metrics in certain key systems. So for example, in this case, there was no guidance on how fast that intermediate turbine blade was spinning. So they made a software change. Rolls-Royce did. The engines were built by Rolls-Royce here in the UK. Software change to introduce a turbine overspeed protection, where if they see that turbine start spinning up, the engine automatically fails and goes into a shutdown mode. They also checked every other engine of that design to see if they had any non-conforming pipes, the little stub section. And surprisingly enough, found 40 of them, which they all replaced and repaired. They also decided that the margins of that were probably too small, so just for good luck, let's go ahead and increase the minimum width allowed from, I think it was 5 millimeter, 7 millimeter for each of the walls of that pipe. But here's the other bit. They also then went through and went through the manufacturing process, and I'm abbreviating this tremendously, top to bottom, to ask, how is it that that mismanufactured pipe got into an aircraft? All the way back to, and they had the inspection records, because one thing you can count on with aviation is there's a record for everything. Every screw, and I'm not kidding. They know where it was made, by whom, and in certain cases, like it's titanium, from materials sourced from where. So they traced it back and actually found that basically within Rolls-Royce there was confusion over the process for when something was out of spec. So this thing had been inspected, had been seen to be offset, but it seemed to be cleared and allowed from the way the original design engineers had communicated the standard to the manufacturing engineers. But what there wasn't was a process to basically go back to the design engineers and say, this seems to conform but doesn't look right. Is this really conformant? And what should be done about it? They also reclassified that particular part as a reliability sensitive. It wasn't considered particularly essential in the aircraft, so that it would not be allowed to have any non-conformance. All right, so with all that, let's bring it all together, land this plane. So 3 key things to take away from today. Develop some DevOps checklists with your team. This is not an individual support. Really look at paired execution Demand it for anything that is a critical operation. A critical operation in your shop is anything that should be anything that can either destroy data or affect a customer or your availability or your revenue source or liability. One place I was working, we had the basic question of, does it mean, a critical operation is anything that means we're going to have to write an apology letter up through survive a lawsuit. If it's anything in that category, then it must be done with at least paired execution. And finally, think through a process or develop a process in your own shop for how you want to do incident investigation and reporting as a value add, not an action of blame or shame, but as something that helps your whole team and process get better. Thank you very much. I appreciate your opportunity to talk to you folks today, and hope you have a great rest of the conference. If you hated this talk, you can tweet to me about it at Kendall Miller, which you saw on the slide, or send me email telling how it was a total waste of your time to kendall@onloop.com. If you have any questions, I'll be sitting up here and kind of walking into the hall if there's anything. Thank you.